All right, I think we'll get started. Just want to thank everyone for joining us right now. We're going to go through ERVs. Today's topic of discussion is going to talk more about the commercial side of energy recovery ventilators. We're going to talk about some of the requirements of energy recovery. And if we go through here, we're going to talk about the ABCs of ERVs. We are going to take a step back. We're going to look at, what an energy recovery ventilator is, how the technology works, what's kind of mandating the standards and codes not only in the city of Chicago, but for lead organization, for ASHRAE, what type of standards are they using to enforce energy recovery usage. And then we'll also talk about some savings and some software programs, because that's one of the main pushers for energy recovery is energy savings and owner savings as far as operating costs. So let's get started. If we talk about the ABCs of ERVs, ERV actually stands for Energy Recovery Ventilator. There's a lot of confusion sometimes in the market. There's a couple different terminologies that are used. There's HRVs in the market. There's ERVs in the market. I've seen TRVs. And basically, ERV stands for Energy Recovery Ventilator. HRV would stand for Heat Recovery Ventilator. So if you see an HRV, that actually is only going to be a sensible recovery of energy. Whereas energy, or an ERV, is total energy. So it's going to be sensible and latent recovery. So ERVs are predominantly what we use in the commercial marketplace. When you get into the residential marketplace, you'll see both HRVs and ERVs used. But like I said, today we will focus more on the commercial marketplace where ERVs, or energy recovery ventilators, are dominant. So what's the purpose of an ERV? Basically, an ERV is designed to provide energy savings in mechanical ventilation system. So anywhere where we're using a large amount of ventilation air, this energy recovery unit is going to recycle energy that we've already paid for the building to heat or cool. So we're going to use the energy from exhausted air, and we're going to capture that and preheat or pre-cool the outside ventilation air that we're bringing in. So essentially, we're preconditioning the outside air using the energy that we've already paid to heat and cool the air inside the building with. That sounds a bit confusing, so we'll break it down one more time. We'll use a diagram. So what we're going to do is we're going to precondition ventilation air. We're going to reduce an outside air load requirement. We're even going to reduce cooling and heating requirements, and I'll explain how we do that. And also we're going to lower HVAC equipment operating costs. Now to kind of explain that, I'm going to show you how a wheel works. Typically, an energy recovery unit in the commercial marketplace is used in a wheel, an energy recovery wheel. We'll go into that detail later, but just for the sake of arguments for this diagram, this is basically how an energy recovery unit works. On the top here, well, let's look at the bottom here. We've got, this is the building side on the left hand of this wheel. This is the building side. So we have exhaust air coming out of the building. And then the top here, this would be fresh air coming into the building. Now, in a typical situation without that wheel, we would have a rooftop with an economizer. We'd be bringing in fresh air from that economizer through the supply air. We'd be, sending exhaust air through some type of exhaust fan. With an energy recovery unit, we capture all the exhaust in the building. We take it through this energy recovery wheel. What happens is we take that return air in the summer. This is a summer example here. Let's say we have 75 degrees in our building. We take that energy, we pass it over this wheel. This wheel is actually spinning between both airflows. So we have our exhaust airflow here. We've got our supply airflow here. So this energy travels on the wheel to the other airflow where we're bringing in hot, humid outside air, 95 degrees. So what happens is this energy travels on the wheel. We're bringing in fresh outside air, which just happens to be 95 degrees. It picks up the energy on the wheel, lowering the sensible energy and the latent energy, essentially cooling the outside air and dehumidifying it. And then we get 81, 68 degree supply air. So normally if we were bringing in straight outside air from an economizer, our rooftop would be saying 95 degrees. Well, now we've pre-cooled that to 81 degrees just by use of a mechanical transfer wheel. We're not, burning any fuel source, or we're not using any energy to actually, heat or cool the air with compression. We're actually just using energy from the building, from that exhaust air, to pre-cool that outside air coming in. Now, conversely, if we look at the winter situation, an ERV is used year-round. This is not just a seasonal piece of equipment. In the winter application, we've got our exhaust air from the building here at 72 degrees, which is an average set point. 72 degrees in the building. We've got an outside air temperature of 7 degrees, which is a typical temperature for Chicagoland area. So the return exhaust air from the building is transferred on the wheel to the outside air fresh ventilation air that's coming in the supply. And we go from 7 degrees of outside air, picking up that sensible energy, to 53 degrees. Now, the latent energy works backwards in winter, where we actually want to maintain humidity in our space. We actually go from a 6-degree wet bulb up to 40-degree wet bulb. So we actually keep the humidity inside the space during the winter, and during the summer we keep the humidity outside of the space. So that's why we call it an energy recovery ventilator. We're getting both that sensible and latent energy transfer. So we're getting the temperature change, and we're getting the moisture in or out of the building depending on the season. So that's what we're doing when we say we're going to preheat or pre-cool that air. So that's the precondition of the ventilation air, right? The fresh air that we would have to bring into a building to meet a ventilation code requirement, that's what we're doing here. We're pre-cooling or preheating that air with the exhaust air from the building. This is energy that we've already paid to heat or cool that air inside our building. Now, if we go to that second bullet point, I said we're going to reduce the outside air load requirement. Now, that's crazy. An outside air load requirement is based on the ventilation standard, correct? Well, now we're bringing in fresh air through the system and preheating and cooling it. We don't have to worry about either 100% makeup air unit or worrying about bringing in extra ventilation and heating or cooling that through our rooftop unit. We're actually heating and cooling it with the energy recovery ventilator. And that's how we're actually reducing the cooling and heating requirement of typically, let's say, a rooftop unit. If that rooftop unit had to bring in ventilation air or some fresh air at 95 degrees, we would have to size that rooftop unit basically to design conditions in Chicago, right? We use -10 or 95 degrees. So we're going to have to oversize that rooftop unit to overcome that fresh, hot, humid air that's coming in. Well, now we've reduced that to 81 degrees. So we only size our rooftop unit for that 81-degree temperature that's going to see coming in. So we're actually reducing the amount of cooling capacity we need out of that rooftop because we don't have to configure it to be able to overcome some of those outdoor air ambient conditions. And so essentially that's going to lower the HVAC equipment operating cost because we're not relying on that quote-unquote rooftop or air handler or other piece of main component to heat and cool that outside air. We're using the energy recovery unit to pre-treat the air before the rooftop unit even sees it. So we'll go a little bit further into that to make it a little more clear. If we look at this diagram here on a psychrometric chart, if we look at this red outlined area, this is the normal temperature and humidity variations that we would see from outside air in our climate zone, right? 0 degrees, -10, all the way up to maybe 100, a little over 100 degrees. So this is the outside air that we would normally see coming into our rooftop unit. With an energy recovery ventilator, we have actually reduced that temperature range, that humidity range, to this blue bubble. So now we no longer have to size our rooftop unit for these peaks up here, the temperature and humidity peaks or lows. We can size our rooftop unit to just handle the small blue bubble, reducing the amount of capacity we have to have available. So the HVAC system itself can actually be downsized to what we would normally typically size for. So if we look at some of the additional benefits, because we see that we're reducing the amount of energy required by the heating and ventilation unit to pre-treat that air or to heat and cool that outside air, we're actually going to reduce the electrical load during peak demand hours. So during the hottest portion of the day, we're using the energy recovery unit to pre-cool that air, taking some of the load off the HVAC system and off the electrical system. We're providing savings, like I said, in all seasons, both summer and winter, preheating and pre-cooling. And it's going to enhance that humidity control. I mentioned that during the summer, it's going to keep the humidity out of the space, and during the winter, it's going to help maintain humidity in the space. So you're not going to take that nice 40% relative humidity inside your space and send it outside. You're actually going to keep that inside the space. because of all these different reasons, because we're reducing electrical load, we're saving energy, we're reducing the humidity points that we have to control, we're actually going to have a very short payback on an energy recovery ventilator in conjunction with the standard HVAC system. So we'll talk a little bit about payback later, but I mean, typically we've seen 2 or less years payback on any type of energy recovery unit, and that's a very conservative estimate. So where can we use energy recovery ventilators? I've kind of given you an introduction on where we're getting the energy savings, what an energy recovery unit does. Where do we want to use these? Where do I want to look at an application and say, you know what, I think an ERV would be a great addition to the HVAC system? Well, when you break it down, anywhere where we have large quantities of ventilation requirements, so you're bringing in a lot of outside air, either for ventilation requirements for indoor air quality, anywhere where you have consistent air changes throughout the building, and also humidity control issues. Anywhere where you have a latent capacity that's an issue during the summer and the winter is a great application for an ERV. And an ERV, because it does have energy savings over the life of the system, it's obviously going to be a long-term investment, whereas the first cost may not be the most appropriate. We're actually going to get the energy savings back over the life of the system. When there's a need to expand beyond a typical rooftop operation. So because rooftop units typically aren't sized to bring in 100% outside air, they're sized to bring in 10 to 15% outside air. So when we're able to cut down on that ambient load, that ambient temperature, and that humidity, we can actually use a rooftop unit where we may not have previously done that. So we get benefits of more latent and sensible capabilities. We have higher efficiencies, lower energy consumption, and more stages of operation from that rooftop system because we can size it properly for the actual phase, and we'll get better humidification control. So when we're looking at some of those applications, anywhere where we see high levels of ventilation requirements, retail stores, schools, offices are great applications. Theaters, where you have high ventilation loads for short periods of time. Fitness centers are obviously huge humidity generators. So we want to maintain that humidity level in that space. Gymnasiums, hospitals, restaurants, and nursing homes. So these are places where we have large amount of ventilation requirements and some humidity issues that we need to control. So we kind of understand what an energy recovery ventilator is. So why now? Why is it in the last 3 or 4 years we've been seeing more and more requirements for energy recovery ventilators and codes and standards, and why is it an ERV a new buzzword in the last 5 to 10 years? Some of the market drivers specifically are the ASHRAE standards. ASHRAE standard 62.1, which was first instituted in 2004, outlined the ventilation for acceptable indoor air quality. So this set a level of ventilation that was required for indoor air quality in each different type of space, like in a school or in a restaurant. It dictated how much ventilation needed to be brought in. So that's our ventilation standard that we're looking at. An energy standard, ASHRAE standard 90.1, which we're all familiar with, is obviously our energy standards for our buildings. And this is what's used for, the LEED certification for the IECC codes. State codes are mostly based on 90.1, and this is going to set our energy standards. So because an energy recovery ventilator helps reduce energy usage, it's going to be incorporated into that standard as well. If we look at the history of ventilation rates in the U.S. market, it's definitely, the amount of ventilation that's been required in commercial buildings has definitely varied over the years. If you go back in time into the 1800s, before the turn of the century, we brought in fresh air as we were building, very loose buildings. Nothing was extremely tight. We had natural ventilation and infiltration coming into a space. When we started coming out with published state codes, around the turn of the century, we were up to 30 CFMs a person. They had the capability to just bring in large quantities of air. As we go into the Depression years, we take a closer look at our energy usage in some of those buildings, and we say, you know what, we don't need to bring in that much ventilation. Came down to about 10 CFM around the time of the Depression, a little after that, 1930s. And it was right around 10 CFMs for quite a while until we get into about the 80s, the early 80s, late 70s, early 80s, when we did a couple of studies on actual ventilation in the in a building and how inefficient ventilation is. Because we're bringing in outside air that now I have to pay to heat and cool, they actually reduced the ventilation standard to 5 CFMs per person. Now, if any of you remember in history, this time during the early 1980s and the mid-80s is when we started seeing lawsuits and claims for the sick building syndrome. This is kind of where that term came out of, because we were reducing the ventilation standards inside those spaces. People are actually getting sick. We weren't properly controlling humidity in the space with outside air. We weren't, providing enough indoor air quality for the occupants in the building. So we were getting those sick buildings, quote unquote, mold issues and other things like that in the system. So when they actually took a look at that, they raised the ventilation rates back to 15 CFMs. And for the next 10 or 20 years, we've kind of been bouncing between, 15 to 20 CFMs per person in the space. So we've kind of honed in on what's a safe indoor air requirement on ventilation, and also what's applicable for the building that we can still maintain a certain level of energy efficiency, bringing in that much outside air. So it's kind of, you can see the history of the ventilation rates. You can see here in 2004 is when they instituted ASHRAE 62.1, which is still our basis for today. They've built on that, but that's when we instituted 62.1. So why now? Right now, what's going on is that the standard 90.1, previous to the addendum E, the threshold was whenever you have a CFM, an outside CFM, or a CFM of a system, 5,000 CFMs, and you're bringing in 70% of that is outside air. So 70% of 5,000 CFMs, if you're bringing that much outside air, you had to have an energy recovery unit. So now, with the recent adoption, the second public review has been complete on addendum E. They've actually changed the threshold where ERVs are required. And they changed the threshold based on regions and size of the system. So not only based on CFMs in the system, but based on the region in the U.S. And that's specifically because of humidity requirements. Because the second part to an ERV system is actually humidity. So they've actually broken that down into different regions, and they've actually added on one more requirement that an energy recovery unit that's used must be at least 50% efficient, or 50% recovery effectiveness. And I'll explain what that means in a few minutes here. But let's take a look at the map, what they've broken down with addendum E. We've broken down requirements into actual regions on the map. If you look here, we've got Zone A on the east side of the U.S. is a moist area. This is where we have some humidity factors we have to take into consideration. On the east side, we have Zone B and Zone C. So we have our coastal climates along the Pacific region, and then we have the west, where we know we have a lot more drier air, drier climate. And then we've broken them down from 1 to 8, going from the southern part of the state up into the colder areas, 8 being obviously Alaska, 7 and 8 being the colder climates. So if we look at the energy recovery requirement, because we're not only using, here we've got the zones on the left, we've got zones here, we've got, the western regions up here, and then here in Illinois we're 5A with the other moist eastern climates here. So we've got it broken up by zone, also, east and west, temperature and humidity zones, and also by percentage of outside air. So let's look at 5A, which is Illinois. If we have 5,500 CFM design in our system, and we're using more, between 30 and 40% of that is outside air, then we're required to use an energy recovery ventilator. Similarly, if you go up, you have 1,000 CFM in your system, and you're using between 70 and 80% outside air in that system, so that's almost 100% outside air in that. Then you have the requirement for an energy recovery ventilator. If you look at some of the other climates, these are the dry coastal climates and the western climates. They don't have that humidity requirement at those smaller CFM levels, so they're actually not requiring that. If you look in the, the next 1B and 2B, if you look over here, 1B and 2B, down in that dry climate area in that Texas, New Mexico area, only when you get up to large CFM ranges, 26,000 CFMs, and you're half of that is outside air when they're starting to require ERVs. So they've kind of broken it down and gotten more specific on when an ERV is really going to provide those energy savings. And we said the part 2 to that requirement is that they have to have 50% total effectiveness. And I'll break down what that total effectiveness actually means in a few slides here. We'll talk about that. Real quick, let's look at one of the other standards that's making a huge impact on our market today. We just see, if any of you attended Greenbuild, you saw a lot of, LEED references plastered all over the place. This is huge right now. Everyone's paying a lot of attention to the green building market and green building standards. So using an energy recovery ventilator, because it saves you so much energy and also increases the indoor air quality because you're bringing in more ventilation, it qualifies for a lot of those different green building applications. So if we kind of break that down, under energy and atmosphere, you can get optimized energy performance on your system because we mentioned using an ERV actually reduces the size of your HVAC system, like your rooftop unit. Instead of maybe previously having to have a 6-ton unit to take care of that, summer and winter load, maybe we can now replace that unit with a 5-ton unit. So we've reduced the amount of our HVAC system, reduced the amount of compression required or heating required using the energy recovery unit. Increased ventilation. Because we're able to bring in more outside air because we're pre-treating it, preheating or pre-cooling it, we can actually increase those ventilation rates without taking a hit on efficiency. So we're actually going to increase ventilation, which increases that indoor air quality, which is a great thing, obviously, for a green design. If we look at outdoor air delivery monitoring under environmental quality credits, under LEED, EQ, environmental quality, we can actually, with these energy recovery units, part of the built-in controls is that we're going to monitor how much air we're bringing in and exhausting. Therefore, we're monitoring the ventilation airflow that's going into the building, which is what the standard is looking for. They want to know how much actual outside air is getting into the space. And we can modulate that based on that CO2 level. So based on the amount of occupants in the building, we can modulate the amount of outside air we're bringing in. One of the other credits is thermal comfort. Because we're handling that humidity, that latent load, we're actually taking a lot of that stress off the HVAC system, or we're getting better humidity control out of the system. We're either pre-dehumidifying or humidifying the space before that outside air comes in. So we're taking a lot of that load off the HVAC system and being able to get better control of the humidity in our space. So that's some of the lead applications of an ERV. So I kind of looked at what an ERV is, why it's important right now, what codes and standards we're actually applying to. Take a look at the technology of an ERV. If we break down the basic systems, we talked about in our initial diagram, we've got exhaust air from the space. So if this top part of the screen here is my building side, this is my building. This black box in between, this would be my energy recovery heat exchange device. It can be a few different things. We'll talk about that. We talked about a wheel being one of them. And then this side right here is our outside air, right? So we have exhaust air from the space coming out, going over that heat exchanger and being exhausted out of the building. We've got outside fresh air coming into this energy recovery device, going over the heat exchanger and into the building. So we've got that fresh air coming in through the HVAC system, going to the HVAC system. And our recovery device is in between those two systems. So we've got two separate airflows. We talked about a wheel being a typical application in the commercial marketplace. An energy recovery wheel, what it's going to do is spin between both of those airflows. So it spins between the return air that passes through the wheel. It picks up the energy in the wheel and spins into the other airflow, where that ventilation air is going to come in, pick up that energy, and go into the building. Now, these energy recovery wheels are going to spin at a very low RPM. Between 10 and 60 revolutions per minute. So that's a really slow revolution rate. We're not using a lot of energy to move that wheel. We're using one simple belt to rotate the wheel. So there's not a lot of mechanical pieces that can go wrong with this system. And it does a really great job of transferring that energy. We'll talk a little bit more about the wheel itself, but that's basically how they work here. I mentioned with the code, there is a 50% effectiveness of an energy recovery device that's required. Now, how they calculate that effectiveness of the wheel itself, of that material, is just basically how efficient the material in that wheel is of taking the energy and transferring it from one airstream to the other airstream. To calculate that percent of effectiveness, We take the change in temperature of one airstream all the way across and the change of the two entering airstreams on either side of the system. So the return air coming in and the outdoor air coming in. How much did we improve that temperature? So in this instance, we had 95-degree outdoor air to 78-degree supply air. And then we had 95-degree outdoor air coming in, and our return was 75 degrees. So how much of that 75 degrees was I able to recoup with that energy recovery wheel? And in this instance, this specific wheel is 82.5% effective or efficient, a percent effectiveness. So that's typically what you'll see of a lot of wheels, 60 to 80% effectiveness. These are really great heat transfer devices. We'll talk about the materials in each one of them. If you look at the winter ventilation effectiveness, it's essentially the same equation. We're just working backwards. The 58 degrees to negative, or to the outside air, the 10 degree to 58 degrees. We reverse the numbers so we don't get a negative. You get 80% effectiveness during the winter. So you'll get a summer and a winter effectiveness off of each wheel. If we look at the energy wheel itself, and so we'll break down the wheel itself so you can see it. This is a basic wheel that you would see in a commercial application. We've got the frame of the wheel itself. We've got the division between the two airstreams, that sealed division here. We've got each of the wheel matrix pieces, kind of like pieces of a pie. Because these wheels can handle large CFMs, they can get pretty large in size, so we break down the wheel itself into little pie pieces that are able to be taken out and put together. This is the exhaust airstream up here, and this would be the supply airstream down here. So I said this support would separate the two airstreams. The wheel would spin in between them. As you can see, there's one of the pie pieces that comes right out. They pop out of the system. Most of the ERVs are about 80% efficient, or 80% effectiveness in transferring energy. All wheels are ARI 1060 certified. Most of them are steel framed with a stainless steel hub and just that rotating wheel component. Permanently lubricated bearings. We'll talk about the desiccant on the wheel. The desiccant is what actually does the latent transfer, but we'll break that down. Fractional horsepower motor, we talked about a really slow RPM on these systems. So we're going to have a fractional horsepower motor, which is not going to use a lot of energy to rotate that wheel. Most of these systems have about a 5-year warranty. Air Exchange is a manufacturer of energy recovery wheels that's used predominantly in most applications. Most manufacturers that are using ERV. Air Exchange is a very common manufacturer of that wheel. Specifically, MicroMetl is one of the companies that Carrier works with and TEC works with. MicroMetl manufactures their own cabinet and then uses the Air Exchange wheel in their cabinet. So each one of their cabinets will have a rating with that Air Exchange wheel. And then when you mate that up with another piece of equipment, then you'll get another rating. We'll talk about that as well. But just you can see some of the CFM ranges on those wheels, anywhere from 0 to 6,000 CFM, I should say. We can do different cabinet sizes with different fan options. So with 14 different cabinet sizes and 33 wheel options, these are the different sizes of wheels here, we get 409 possible configurations. So we're using different wheels and different cabinets to match the exact CFM, supply and exhaust airflow, on your application. So MicroMetl will be the company that will put those two combinations together to fit your size requirement and your CFM requirements. Just a quick breakdown on enthalpy wheels versus sensible heat wheels. I mentioned heat recovery ventilators. There's also those sensible wheels. These actually just transfer your sensible energy or affect the temperature in a space. So if you look on the right, obviously we're just moving along the sensible energy line of the psychrometric chart. We're just changing temperatures from 1 to 2. We're preheating or pre-cooling and not addressing any of the latent energy or the humidity in the space. A total energy recovery wheel, meaning sensible plus latent, or an enthalpy wheel, which is most ERVs and energy recovery, would mostly be an enthalpy wheel, where it's actually adjusting the temperature as well as the humidity. How do they do that? How does the wheel actually transfer humidity from a space? Well, these wheels themselves are made of a plastic polymer. So this is a plastic polymer. It's got little divots in here that allows airflow in between. You can kind of see very small, thin pieces of plastic packed very tightly together here, about a ½ inch. And these little, these plastic pieces in these segments of the wheel are lined with a desiccant. The desiccant is actually like a silica gel. If you think of like your shoe boxes or ladies when you buy purses, there's that little packet of silica in the bottom. You know, do not eat this, the packet, what it says. What that silica is in there for is to absorb any moisture in that box to prevent your item of your item from getting wet or getting moist. A silica or a desiccant has pore openings, chemically has openings that allow moisture to be brought in. It absorbs and releases moisture very quickly. And so that's why they use different types of desiccants on these wheels to absorb moisture and then release it. There's different desiccants, there's different types in each one of wheels, but basically how it works, here's a chemical breakdown of a desiccant. The water vapor molecule goes inside, fits inside those absorbed into the desiccant itself, but the water vapor pressure from a colder exhaust air kind of releases that moisture back into the space. So the desiccant opens up with that colder air and releases the moisture back into the space. So it kind of absorbs the moisture and then releases it again. And there's different types of desiccant materials, but a silica is one of the most common. As we talked about the segmented wheel. These wheel pieces not only are segmented for installation, but also for cleaning. We're going to pre-filter the air, but basically we want to keep that wheel clean, make sure there's nothing, as you can see, those plastic polymer fibers are pretty close together, those plastic sheets there. So we want to take those out at least once a year. You can bring them out, hose them off with a non-acidic cleaner or an alkaline detergent solution. Most of these are, if you're lucky enough to get a hose on top of the roof, you can bring them out and just pull the most wheel cabinets slide directly out of the ERV. You can just spray them down. It's very easy to clean. So we talked about the wheel itself. Let's talk about arrangement of an ERV, because this is also critical when we're installing an ERV in a system. When we put these airflows together, inline recovery device, meaning that we're taking the supply and return airflows next to each other with an inline device between the two, is the most common application of the ERV. When we do that, there is filtration requirements. When we're bringing in the outside ventilation air and we're exhausting air from the building, we want to pre-filter those two air streams to make sure nothing gets on the wheel. That filtration is just meant to protect the wheel. That is not for indoor air quality. That should all be handled by your heating and ventilation piece of equipment, your rooftop or air handler. These filters on the system, they're actually protecting the wheel, making sure those polymer fibers aren't clogged with any gunk or, leaves or anything like that. So that filter is just to protect the wheel itself. The wheel blower arrangement, how we're pulling air across that wheel that's sitting between the two airflows, is actually very critical as well. There's a lot of different designs. If we look at designs that we should not use, if you push air outside of the building and push air in, if you do a push-through design, we actually have more of a chance of carryover or leakage between the system. And I'll define what that means. If we kind of look real quick at this leakage slide, leakage basically means when I'm sending air, exhaust air from the building out of the wheel across outside of the building, some of the air obviously wants to follow the path of least resistance. So instead of going through that wheel, it actually is going to creep around and sneak around before it actually goes through the wheel and get back into the supply airstream. So that's bad because we're not getting as much ventilation air as we need to, right? We're just returning air back into the system. Conversely, we can get outside air that is coming in from the space. It doesn't want to go through the wheel, and it can actually go back into the exhaust air. So that fresh air actually is just going to go back and be exhausted from the building instead of going through that wheel. And if I go back, that's because of these blower arrangements. The ideal blower arrangement is going to be a push-through and a pull-through design. So if we're pulling the airflow across that wheel, it's going to be less likely to go down on the other side of that wheel, that supplier, or that exhaust air from the building coming out. So we're going to pull it through the wheel, and at the same time, we're going to push through air into the system, which isn't going to draw that air. If we had that push-through, pull-through design on the opposite, this second fan here is actually going to want to pull that exhaust air from the building around. So we want to make sure that we have a pull-through, push-through design, so we're getting all the exhaust air out of the building and actually maximizing that, or reducing the amount of leakage in the system. So there's a specific design to the motor inside the energy recovery unit system. And whereas we said an inline design, an ERV is usually a packed piece of equipment, but doesn't always need to be. Commonly with air handlers, we're using energy recovery devices or heat exchangers in line with an air handler. So sometimes these blowers, we need to be aware of how we're pushing and pulling the air over that energy recovery type system. Now, in instances where we do get leakage, there is a way that we can use a purge type fan or purge angle to reduce that leakage. So if we use a purge angle, it actually, so if we look at the exhaust air out of the building on the top of this energy recovery wheel and then the supply air into the building, as I said, we had a pull-through fan and a push-through, a pull-through on the exhaust air of the system, a push-through fan on the bottom. Or that air is coming across, some of the air is diverted up and along the inside of the wheel. So it's going through and up and then back out. And this is actually pushed through the wheel and up to prevent any of that return air coming down. So that reduces any cross-contamination of return air into fresh supply air. So that air coming up would push that air across the wheel and prevent it from coming down back into the supply. That essentially reduces that cross-contamination or that energy air transfer. Energy air transfer is kind of the term that they use for leakage. So it's EATR, energy air transfer ratio. It's the amount of air that we actually, that sneaks into the system or out of the system before going through the heat exchange wheel. Frosting is another issue. So we had motor location we want to be aware of when we're installing energy recovery units, and also frosting. Because we are bringing in a cold during the winter, we're bringing in cold outside air, and we have warm inside air coming out, there is a potential for frosting in those colder climates. So if we look in a situation where it had negative 5-degree outside air, and we're bringing in 75-degree inside air at 45% relative humidity, 45%, we actually cross that dew point line and we can get frosting on that energy recovery wheel. We obviously do not want to freeze our wheel because we're going to lose all efficiency in the system. So there's a couple things that we can do normally. We can actually pre-treat our humidity, which would bring that line down as well, or we can preheat that outside air. So we can do some type of heating of the outside air, do an electric preheat before the coil to reduce that as well. But most typically what would happen is that in a frosting situation, we could shut off the outside air coming in. We would recirculate that inside air to defrost the wheel itself before we brought in more outside air. There's a couple different ways to take care of that, and we would do that with the design itself. Some wheel frost control obviously is required for colder climates. Enthalpy wheel has the lowest frost threshold because it has a way to mitigate some of that humidity. Some of the frost control methods that I just mentioned were an outside air electric preheater. So you can actually preheat the air coming in, so that would obviously raise this, that would move this entire line over, therefore we wouldn't be crossing that dew point line. ERV wheel VFD. So what we can do is we can actually slow down the rotation of the wheel, meaning that more of that return air would have a longer time to defrost that wheel. The frost protection is when the outside air shuts off. We close the dampers to the outside air, allowing a recirculation of the exhaust air in the wheel, so that would defrost the wheel as well. Or we can have a low temperature lockout, so whenever we do go below that threshold with that humidity level, we can lock out the ERV itself and just go into a full economizer mode, or reduce that to the minimum ventilation requirement for that space. So we talked a little bit about the technology of the wheel itself. Let's talk about the cabinets and mating. So how do we get this energy recovery system to mate with the HVAC system? How does that actually work, and where do we get our ducting and everything? Here's a picture of a typical packaged roof-mounted energy recovery ventilator, an ERV section. Right here we actually have the wheel is laid on its side here. So the wheel is flat in this space. It would actually slide right out right here. This cabinet would open up. We've got our supply and return exhaust flows with our hoods here, in our controls or our fan speed settings, we'd actually use a roof curb type system. In most packaged ERVs, we'll talk about that curbing system in a second here. With most packaged ERVs, they can be direct drive or variable speed or even an ECM type motor. Usually high efficiency fans are used. We have the capability to actually dial in the amount of airflow in the system, allowing us to balance the airflows. We can adjust the wheel effectiveness, take the higher recovery rate based on our CFM, the CFM of the system. We can do a double wall insulation on the ERV itself. 5 to 10 years, usually warranty on the heat exchanger itself. ERVs, just like any other rooftop unit, we can always custom paint them. A lot of different control options that we can build into an ERV system. Maintenance indicators, we talked about LEED for CO2 and space sensor control operation. The electric preheat, frost control, we can motorize all our dampers. We can integrate into the GDC system, so it can actually integrate directly into any other front end in the system itself or the building. There's a couple different ways that we can duct this ERV air into the space, right? How do we get that outside ventilation air through the ERV and into the space? There's two main ways that we can do that. Basically, we can take the dedicated outside air approach, where here we have our ventilation air coming in. This is our ERV system, taking that outside air directly into the space. Here's an energy recovery unit on a dedicated outside air system. So we're actually we're fully tempering that outside air. We're obviously preheating and pre-cooling it, and then we're completely tempering the air to go directly into the space, separate from our HVAC system, when we're decoupling our ventilation requirement from our space load requirement. In that instance, that HVAC system would just be maintaining the load requirement in each space. Conversely, we can actually connect that ventilation system to the HVAC unit. So we have just the ERV unit on the space, recovering the exhaust air, bringing that ventilation air directly into the HVAC system, whether it be a rooftop unit or a fan coil or an air handler. This, we would bring that in, mix that with return air, and then we would size the HVAC system to completely temper that air from that 81 degrees down to the 75 for supply into the space. Oh, excuse me. So we can actually bring that ventilation air, that pre-treated ventilation air, into the HVAC system and then size it to do the rest of the job. Obviously, this HVAC system isn't going to be seeing that 95-degree outside air. It's going to be seeing 80 degrees, so we don't have to fully size it for outside air. We're going to reduce the size of the HVAC system that we talked about before, but it's going to be still sized to temper that ventilation air along with that return air for set point requirements. If we are duct mounting the ERV unit, as I said, we can put it in a packaged outside system. We can put it indoors, duct mounted, air handlers, things like that. The ERV wheel selection and the frame would be all that you're selecting. So you would actually have this frame box with the wheel inside, and you would mate your 2 or your 4 airflows here, your supply connections and your return connections. The standard installation is with a packaged rooftop unit and an energy recovery unit ducted together. There's a lot of different ways that we can do that ducting, but here is what it would typically look like, a horizontally ducted system. So we had our exhaust air, return air coming out of the rooftop unit through the ERV, our fresh supply air coming in across the heat exchanger and that ERV into the rooftop unit to be fully conditioned for the space load. There's a couple different ways we can do that ducting. Obviously, it's all horizontal ducting. We can bring directly into the system for an ERV transition, and we can have a return air directly separated. So we can bring in direct economized return air, or we can bring return air through the ERV. Another way we can do our ducting inside the building. We can actually lay our rooftop equipment and our ERV on the roof, and we can do our ducting inside the building below the roof line. So here you can see we have our exhaust air going out through the ERV unit, fresh supply air coming in back into the building, back into the building here, and then over to the rooftop. So we can actually do that ducting below the roof of the building itself. Or we can do it in a roof curb. We use commonly with MicroMetl a combination roof curb. So this is what we call for short a combo curb. And what it would actually be one single roof curb that we would lay on the roof that would actually drop the energy recovery unit onto that curb, as well as the rooftop unit onto the curb. And that horizontal duct transition is built into the roof curb. It's built in to reduce the static hit that we would take in the system. So they build in that transition into the system. So we take return from the building into the roof curb, out through the ERV. That fresh air would come in through the ERV, going into the roof curb, and back into the rooftop unit, or HVAC system itself, and into the building. So that's obviously the most common, is that combination roof curb. Here's a picture of a direct installation of that. You can see this, the flashing on the roof right here. You can see this combination roof curb, and then we drop the rooftop unit on, and the energy recovery unit directly on, and all that duct transition is done inside that roof curb. So it's a very easy installation, especially for new applications, even for retrofit type applications. A single roof curb that you drop on both pieces makes it a really quick installation. Very easy to do. There was also bolt-on ERVs. So this would be your rooftop piece of equipment where you're supplying your economizer and your exhaust hoods would normally be here. We would remove those exhaust hoods. We'd actually bolt on an energy recovery wheel to the side of the rooftop equipment. This is primarily for, rooftops maybe 5 tons or less. So 2, 3, 4, 5 tons are small enough to have a system like this bolted on. The nice thing is that you don't have to worry about the roof curb below this system. It's small enough and light enough to just bolt directly onto the rooftop unit. So that would actually, you'd have the optional economizer and power exhaust function with the system bolted onto the rooftop unit itself. With that bolt-on, it's kind of a neat. Here's a different layout of the actual bolt-on. So you can see it's not curbed in with the other rooftop equipment. It's actually bolted on the side. Our energy recovery wheel is vertical here. We would have outside air coming in across the wheel into the rooftop unit. We've got return air from the space, either going directly into the unit itself, or depending on the mix of return air, CFM and exhaust CFM, we can bring that back through the wheel, out exhausted into the outside air. So we've got the exhausted air coming through the ducting into the unit, out the exhaust of the system, out the exhaust of the rooftop unit through the ERV, and then that fresh air coming in across the ERV into the rooftop unit itself. So you're still getting that mixing based on your, how much CFM you're exhausting. You'll still get that air mixing the system directly in the rooftop unit. Some of the other standards and codes, we've talked about the layout of the system, the ERV unit itself. ERVs are regulated by ARI 1060. It's that performance rating for ERV equipment. Only ERV components that have been independently tested can actually have this seal. So if you are purchasing ERV equipment, look for that ARI performance certified standard on all your ERV equipment. That is the rating firm for ERVs. Obviously, we mentioned ASHRAE 62.1. This is going to regulate the ventilation requirement for acceptable indoor air quality. So this is what's going to dictate how much outside air you have to bring in. It'll tell you your minimum ventilation rates for your indoor air quality. It's going to classify the amount of air that you're exhausting from the space and when you can use the energy recovery ventilator. And then you can use the energy recovery, which allows your air to be reclassified based on dilution. So they've classified air in a few different ways. As we look at those classifications, you have Class 1 through Class 4. Basically, Class 1 is just return air that can be recirculated back to the system. It's inoffensive with no odor, basically, is what it means. Class 2 is moderately contaminated air, mildly offensive odors. Class 3 and Class 4 are kind of, paint booth type equipment, air that has to be exhausted directly from the building. So this code of 62.1 is going to tell you when you can bring that return air and actually use an energy recovery ventilator. If you have highly objectionable air, like Class 4 air, you may not be able to use an energy recovery system on that exhaust air. So that standard would help classify when you can bring that recirculation air back through. The air classification recirculation, it dictates when an energy recovery unit can bring Class 2 air to Class 1. Class 2 air may be redesignated as Class 1 air in the process of recovering energy when it's diluted with the outside air, no more than 10% of the returning air stream. So we can use 10% return air with some, unbalanced or fresh air coming in, we can dilute that air so we can actually change the classification. They've also finally talked about toilet exhaust, which is specific, and I'll go right to the City of Chicago code, because the City of Chicago code is very specific on toilet exhaust. This applies to you. Toilet exhaust is not able to be used in recovery applications. You can't use toilet exhaust in a wheel recovery application. I'll kind of comb through some of this code lingo. But you can use a fixed plate heat exchanger in the City of Chicago because of the transfer ratio. We didn't talk specifically about the fixed plate heat exchangers, but a fixed plate heat exchanger would actually provide zero cross-contamination because of the airflows between the two systems. So in those applications, we use fixed plate. But there are applications where we can use a purge angle to get zero transfer, the entering air transfer ratio to zero for a lot of those wheels. So the way the code in the City of Chicago is written, so seating cycles directly exhaust air from outside the atmosphere should not be connected to any exhaust system from which recirculating air is forbidden under this chapter. So we can't use toilet exhaust in a wheel application, but we can use a fixed plate heat exchanger because it provides that zero crossover ratio. And if you have questions about that, feel free to send me an email. We'll talk about those fixed plate cores a little more in detail. Today's topic was just basically on commercial energy recovery ventilators. Fixed plate cores, just as a sidebar, are usually used for a smaller CFM size. Each fixed plate core usually is designed for about 500 CFMs. You can bank multiples of those fixed plate cores to go up to 2,000, 2,500 CFMs, but then it becomes cost prohibitive. Unless you're in the City of Chicago where they require you to use those fixed plate cores anytime we're using toilet exhaust as part of your exhaust from your building. But predominantly in the commercial marketplace, you're using a wheel application, which is the topic of our discussion today. So if we look at some of the energy-saving software programs, a lot of manufacturers have free performance software for energy recovery units themselves. For the air exchange wheels themselves, they provide software. This is the air exchange software where we would actually type in the amount of CFM that we're supplying and exhausting, whether it be balanced or unbalanced. We'll give our outdoor air conditions, our return air conditions of the system, and it would actually, we would select a specific wheel model, and it would give us what we would get on our entering air temperature conditions. So during the summer, we would go from 95 to 79 degrees with a specific wheel. In the winter, we go from -10 to 66 degrees. So that's the amount of recovery we get with this system. It would show us our design loads, and it would help establish recovered loads, how much we're actually recovering from that exhaust air. So this is efficiencies of the wheel itself, from that air exchange wheel. MicroMetl Corporation would take that air exchange data on the wheel, use it in their combined cabinet. So once we combine that into a cabinet, that EVDD wheel that we talked about in that previous slide, this is the EVDD wheel. We would combine that with the specific cabinet from MicroMetl, and then we would have our complete combined energy savings, our cooling savings, our heating savings. So this is, and a heating savings is basically the amount of energy that we're able to extract out of the exhaust air. But that translates as savings because that's less heating that the HVAC system has to do. So we save energy on the HVAC system, and that's where those savings come in. Once we get those two pieces of equipment, we can add on the unit itself, the HVAC system, and get a combined efficiency. We can get a system EER on the air exchange component with the cabinet plus the unitary piece of HVAC equipment as well. So we can combine all those pieces and get a combined system EER. There's different system ratings for all these combined pieces of equipment. We have ARI Guideline 5 actually gives the outline of how to rate these combined efficiencies. So it's applied efficiencies and performance of ERV equipment. So it's ERV equipment plus that HVAC system, and gives us a combined efficiency, a CEF value. So it's basically the net cooling delivered divided by the total power consumed. So it's the net cooling of the energy recovery unit plus what the rooftop unit or HVAC system has to do, divided by how much power is actually used. And if we're preheating or pre-cooling that air with the ERV, that's obviously less compression and less electrical usage we have in the HVAC system. So inherently we'll get higher EER values with those combined systems. If we take a quick look, just on average, we've got a couple different areas. We look at Indianapolis, on an average 10-ton rooftop system with 4,000 CFM of outside air, we get an average combined efficiency of 21.9 EER. Now that's significantly higher than your standard rooftop unit, which is maybe anywhere from 10 to 13 EER. So you're getting much higher combined efficiency values, which are outlined in this guideline on how to calculate. And that's where you're getting the energy savings, and that's what applies to that LEED type of credential towards your building. There's also individual savings calculators where we can provide the software to you, but it's very basic. You actually enter in the energy recovery value cost, your initial cost, the cost of the combination curb, build in, your annual maintenance over the life of the system, the labor for installation, and then based on a 15-year, payback, we'll give your monthly paybacks and your energy cost. In this specific example, we had a 2.1-year simple payback. So a 51% internal rate of return on this investment. So if you look at, if you take that to a market analysis, what other piece of investment can you make to get a 51% internal rate of return? So, if you look at it, from a bird's eye view, this is a really great investment for your business or for your building. We've broken down multiple different CFMs and cabinets and what we've seen as an average tonnage reduction and heat reduction on the system. So in all the different applications and jobs that we've done, we've kind of summarized conditions for, central Illinois, so anywhere from 500 CFM to 20,000 CFMs. You can see a 5,000 CFM system on average, 5,000 CFM of outside air. Let me clarify, that's 5,000 CFM of outside air coming in through the ERV. We could reduce the cooling tonnage requirement of the HVAC system by approximately 13 tons. So anywhere where you have 5,000 CFM of outside air, you can actually reduce that cooling requirement on the HVAC system. So that's going to save you energy and money up front if you're replacing that system. And that's not only the real story. We know that in our area, it's all about the heating. That's where, a lot of the dollars go into heating a building. And we can save over 400,000 BTUs of a heating in the system. So that's 400,000 BTUs less that our HVAC system has to do. So we can reduce the amount of heating capability of that system. And we're still getting those conditions off our summer and winter conditions, 79, almost 80 degrees off the wheel, 51 degrees in the winter. That's huge to go from 0 to 51 degrees. That's a huge amount of energy savings, which relates directly to that 400,000 BTUs. So we're going from 0 to 50 degrees. In this specific instance, most of the time with 5,000 CFMs of outside air in our area, we're going to see a 0.6-year payback. So that's about 6.5, 7 months of payback we're going to see on our system. So that's our, the investment return. If we break that down into actual dollars, it's $5,000 of savings over the life of the system, over an annual savings of that system. So we've broken that down. We've got some of the values just to give you an idea of how remarkable and how amazing the payback is on a simple ERV system. It's a very basic component that we can add to, something as simple as a rooftop unit on a building that uses a lot of ventilation for the space load. And we can get some serious savings. So a lot of retrofit applications are perfect candidates for ERVs, and even your new construction applications. Now, because of some of these, I'm going to flip back and forth, because of some of these payback years, anywhere from 2, to 0.1, that's about, 2 months or something like that, payback on the system. Because we see a product, anywhere that a product has less than 2 years on payback, it's obviously a great candidate for commercial leasing. With the economy in the state, and getting more and more customers to retrofit some of their buildings, equipment leasing is a great option for you and your customers. I mean, most office buildings lease, their furniture, their copy machine, their, desks, chairs. They lease a majority of their equipment in their building. Why not lease their HVAC equipment as well? So on an item that actually has a less than a 2-year payback, the monthly recovery on energy and utility from an energy recovery unit can actually be enough savings to pay a monthly lease. So that's why we target equipment like ERVs for equipment leasing. You can actually get a payback greater or equal to your monthly lease on the equipment, and it can pay for itself. Commercial equipment leasing is very easy as long as you have a commercial customer. A contractor itself can set this leasing up between Irvine, which is the primary partner that we use, and the agreement is made between Irvine and the customer itself. So if you're the installing contractor, it's great for you because you actually get paid up front, and then the agreement is between Irvine and the customer. And then at the end of the lease, it would be a $1 buyout, and the customer itself would they would own the piece of equipment. So it's a really great option I just want to bring up because an energy recovery unit has such a small payback, or such a great payback in a small amount of time that it's a great candidate for commercial leasing. So I just want to throw that out there. So with that, don't want to go too long on time, but wanted to wrap that up so you guys could just see there's so much to talk about with ERVs and so much, qualifications for some of the green building standards, for ventilation, for indoor air quality, and for building savings as well and operating costs. There's a lot to talk about. That's why we kind of focus on just the wheel itself today, the ERV wheel. But if you have more questions, please email me or feel free to give me a call directly. We can talk about fixed plate cores or Chicago code or wheels themselves. We can go a little bit deeper into some of that discussion. But I hope you got something out of the topic today. And like I said, feel free to email or call me with any questions. Thank you so much.